Hello, I'm glad you're here. Whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science, this video is made just for you. Tonight, we'll be gently gliding through the cosmos to uncover one of the strangest truths in physics. Why light, of all things, has a speed limit. But before we begin, I'd love to know, where in the world are you listening from? And what time is it where you are right now? Are you winding down under city lights or nestled somewhere quiet and dark, perhaps with a cup of something warm? If you enjoy these sleepy explorations with Stellify Science, please show your support by giving this video a like and tapping the subscribe button. Your support is what helps more curious minds find this calm corner of the cosmos, and it allows me to continue creating these journeys for you. Now, I do hope this video isn't too interesting. If it does accidentally keep you awake, at least you'll come away knowing a bit more about how our universe works. Not such a bad trade, really. So settle in, close your eyes if you like, and let's take a slow, thoughtful wander through the story of light and why it's in such a hurry. Light is one of those things we all think we understand until we actually try to explain it. You flip a switch, and there it is. It fills the room, lets you see your cat's judgmental stare, and makes your phone screen glow long after you swore you'd put it down. But what is it really? Is it a wave, a particle, or a cosmic courier with a very strict delivery schedule? The short answer is yes, and also, sort of. Let's take a nice, slow wander through what light actually is. Because before we can understand why it has a speed limit, we first need to understand what's actually doing the speeding. First, let's talk about photons. They're the tiny packets that make up light. Imagine them as little messengers, zooming through the void at the fastest speed allowed by the universe. But these messengers are strange. They aren't particles in the traditional sense, like marbles or peas. They don't have mass. They don't rest. And they definitely don't follow the usual rules. Now, here's where it gets fun. Photons are also waves, but not waves like ocean waves. They are electromagnetic waves, vibrations of electric and magnetic fields that oscillate at right angles to each other and to the direction they're moving. Yes, it sounds like a physics yoga class, but the mental image is quite elegant. Two fields dancing through space together, locked in a perfect rhythm. These waves don't need a medium to travel through. Most waves, sound waves, water waves, need something to move through. Sound needs air. Water waves need, well, water. But light just goes. It travels through the vacuum of space without a problem. That's why we can see the sun, which is over 90 million miles away. Its light has traveled through the emptiness of space to reach us without a single rest stop. And it doesn't just come in one flavor. The light we can see, what we call visible light, is only a tiny part of the electromagnetic spectrum. Imagine a piano that stretches for miles. Visible light is just a handful of keys in the middle. On one end, we've got radio waves, long, lazy undulations. On the other, we've got gamma rays, sharp, high-energy spikes usually found in the company of exploding stars. In between, you've got microwaves, infrared, ultraviolet, and X-rays. Despite all these differences, all these forms of light move at the same speed in a vacuum, roughly 299,792,458 meters per second. That's just under 300,000 kilometers every single second. To put it in bedtime terms, if light were a runner, it could jog around the entire Earth more than 7 times in a single second. But here's something else to keep in mind. Light doesn't always go that fast. When it passes through something like water or glass, it slows down. Not because it's tired, but because it's interacting with the material's atoms. This slowing down is what causes refraction, the bending of light that makes a straw look bent in a glass of water, or a diamond sparkle so brilliantly. Even though light slows down in these materials, individual photons still travel at their top speed between atomic interactions. They're just taking a more complicated path, like someone speed walking through a crowded dance floor. As if all this weren't already wonderfully strange, light also has no rest mass. Unlike you or me, it doesn't need energy to move. It always moves. If a photon were to stop, it wouldn't just be taking a break. It would cease to exist. It's motion or nothing. So we have these massless packets of energy that behave like both waves and particles, that travel at a universal speed and deliver the very experience of sight and color to our brains. Light isn't just what helps us see. It's how the universe whispers its story into our eyes. Let's take a gentle step back in time. For most of human history, people believed that light moved instantaneously. You lit a candle, and the room lit up. No delay. Even the ancient Greek philosopher Empedocles, one of the few to suggest that light might have a finite speed, wasn't taken very seriously. Aristotle thought light was instantaneous, and for centuries, that was that. But then came Galileo. Around the year 1638, he tried to measure the speed of light in what might be the most adorably optimistic experiment in history. He and his assistant stood on hilltops about a mile apart, each with a covered lantern. Galileo would uncover his, and as soon as his assistant saw the light, he would uncover his in return. Galileo would then measure the time between sending the signal and seeing the return flash. Of course, light takes less than a 10,000th of a second to travel a mile, while human reaction time is about a quarter of a second. It was like trying to measure the speed of a bullet with a sundial. Galileo concluded that if light had a finite speed, it was far too fast for him to measure. But at least the question had been asked. Fast forward a few decades to a Danish astronomer named Ole Romer, who in 1676 accidentally stumbled upon the answer by watching the moons of Jupiter. Romer was tracking the orbit of Io by carefully observing when Io disappeared behind Jupiter, and when it reappeared, he noticed something odd. The timings weren't always the same. Romer had a brilliant thought. What if the delay was caused by the fact that Earth was sometimes farther away from Jupiter, and the light from Io had farther to travel? From these timing discrepancies, he estimated that it took light about 22 minutes to cross the diameter of Earth's orbit. His estimate wasn't perfect, but it was revolutionary. It told the world, light takes time. Later, in the early 1800s, a physicist named Hippolyte Fizeau tried something more earthbound. His method involved a beam of light, a rotating toothed wheel, and a mirror placed several miles away. By adjusting the speed of the wheel, he could figure out the point at which the returning light beam was blocked by a tooth. Using the known distance and the wheel's speed, he calculated the speed of light to be about 194,000 miles per second. Not far off the modern value. Another scientist, Léon Foucault, refined the technique using rotating mirrors, improving the precision significantly. He showed not only that light has a finite speed, but that it actually moves slower in water than in air. But perhaps the most iconic name in all of this is Albert Michelson. In the late 1800s, Michelson fine-tuned Foucault's method to a level of accuracy no one had achieved before, earning him the Nobel Prize in Physics in 1907. Today, we have lasers and atomic clocks. We've defined the meter itself based on the speed of light. Since 1983, The meter has been officially described as the distance light travels in 1,299,792,458th of a second. We no longer measure the speed of light. We use it as a standard to measure everything else. The speed of light isn't just a number. It's a story of curious minds, imperfect tools, and elegant persistence. So, why doesn't light just go faster? Why 299,792,458 meters per second? Why not a nice, round 300 million, or just infinite? To understand this, we need to visit a man named James Clerk Maxwell. In the 1860s, Maxwell took everything scientists knew about electricity and magnetism and turned it into 4 beautiful mathematical equations. When Maxwell combined these equations, he discovered they predicted a type of electromagnetic wave that would always travel at a specific speed. When he did the math, plugging in the known values, he got a number: 299,792,458 meters per second. Maxwell was stunned. He'd found a fundamental speed buried deep within the laws of electricity and magnetism. That number matched the best available measurements for the speed of light. This wasn't a coincidence. It was a revelation. Light, Maxwell realized, was an electromagnetic wave. Its speed isn't a habit. It's built into the equations that govern the fabric of reality. But now, let's go one step deeper. Why can't anything go faster than that? To find out why, we need to call in someone you've probably heard of: Albert Einstein. In 1905, Einstein published his special theory of relativity. One of its key ideas is this: the speed of light in a vacuum is the same for all observers, no matter how fast they're moving. That might sound tame, but it's actually bananas. Imagine you're on a train moving at 90% of the speed of light and you turn on a flashlight. You might expect the light from your flashlight to appear to move faster for someone standing on the platform. But nope. Both you and the person on the platform would measure the speed of that light beam as exactly the same. To make that possible, reality has to bend itself. Time slows down, lengths contract, and mass increases. The universe changes the way it ticks to ensure that no one, no matter how fast they go, can ever observe light speeding up or slowing down. As you approach the speed of light, your mass trends toward infinity. That means you would need infinite energy to reach it, and so, no matter how hard you try, you can get close, but you'll never quite get there. You can chase the light, but you'll never catch it. That's why the speed of light isn't just the speed of light, it's the cosmic speed limit. And here's a peaceful thought. If the speed of light weren't limited, causality, the idea that causes happen before effects, would break down. You could theoretically see an effect before its cause. The universe protects us from that kind of nonsense with this beautiful little speed cap. It keeps things ordered, predictable, and calm. When Albert Einstein introduced his theory of special relativity in 1905, he rewrote the rules of physics. At its heart was that bold statement: the speed of light in a vacuum is absolutely constant for everyone, everywhere, always. This breaks everything you think you know about motion and time. In the everyday world, speeds add up. If you're walking on a moving sidewalk, your speed is your walking speed plus the speed of the belt. But with light, the speeds don't add up. The light speed stays the same. So what gives? Einstein's solution was beautifully unsettling. It's not the speed of light that changes. It's everything else: time and space. First, time dilation. The faster you move, the slower time passes for you compared to someone at rest. This is a real, measurable effect. If you took a trip on a spaceship traveling at 90% of the speed of light, You might return to Earth to find that decades have passed for everyone else while you only experienced a short trip. Next, length contraction. When you travel at high speeds, objects in the direction of your motion appear shorter. Your spaceship would literally measure as being shorter along its path of travel. Then, there's the relativity of simultaneity. This means that two events that seem to happen at the same time for one person might not happen at the same time for another if they're moving relative to each other. Both observations are correct. Time and space are no longer universal. They're flexible, local, and relative. All of this strangeness, time stretching, distances shrinking, happens to protect that constant speed of light. It's as if the universe looked at this one number and said, everything else can bend, but this must not break. This cosmic speed limit is what protects our sense of before and after. Because information can only travel so fast. You can't see an event before it happens, and you can't send a message into the past. Light's speed limit keeps the universe logical, predictable, and tidy. Today, GPS satellites rely on Einstein's equations to work. Particle accelerators use them to guide subatomic particles. All of it rests on this strange but constant truth. Light has a maximum speed, and that speed is the same for everyone. So, what does this cosmic speed limit actually do to reality? Let's start with time. The speed limit gives time a structure. It draws boundaries around what can influence what. Physicists call this the light cone. Imagine you light a match. The furthest anything can be affected by that match is limited by how far light can travel from that moment onward. If something happens outside your light cone, it's not just too far away, it's too far away in time. No signal from that event can reach you yet. It's as if it doesn't exist for you. This idea shapes our entire understanding of the universe. There's no such thing as instant communication or a perfect, universal now. Think about how this affects your view of the night sky. When you look up at the stars, you're not seeing them as they are. You're seeing them as they were. The light from the nearest star system, Alpha Centauri, takes more than 4 years to reach us. The light from the Andromeda Galaxy takes over 2 million years. You're seeing it as it looked when early humans were just starting to figure out how to make tools. This delay is what allows astronomers to be time travelers. Every telescope is also a time machine, peering into epochs long gone. All of this insight is possible because light doesn't move instantly. Its limit gives us access to the past. It also enforces causality. You can't influence something unless there's time for a signal to get there. It prevents paradoxes. Without this speed limit, you could, in theory, send a message to your past self. But with the speed of light as a cap, those logic loops never happen. This structure affects more than distant galaxies. When Mission Control sends a signal to a Mars rover, it can take up to 20 minutes to arrive. The rover has to be autonomous because the speed of light says, "You're on your own out here." It might sound like a constraint, but really, it's a kind of harmony. The speed of light gives us a universe where effects follow causes, where the past is fixed and the future is waiting. You might be asking, well, what if we just ignore the speed limit? Could anything ever go faster than light? Let's start with a curious idea: tachyons. These hypothetical particles were dreamed up to only travel faster than light. There's just one small problem. No one has ever found one. Most physicists agree they are fun to think about, but probably not real. What about quantum entanglement? When two particles are entangled, measuring one seems to instantly affect the other, no matter how far apart they are. It feels like a cosmic cheat code But while the connection is instant, it doesn't transmit usable information. You can't use it to send a message. The universe is spooky, yes, but still respectful of the speed limit. Then there's Cherenkov radiation. This happens when a charged particle moves through a medium like water faster than light can move through that same medium. Remember, light slows down in materials like water or glass. If a particle moves faster than that reduced speed, it creates a kind of light shock wave, similar to a sonic boom. This is what causes the eerie blue glow in nuclear reactors submerged in water. Nothing is breaking the universal speed limit, just the local one. Could we build a warp drive? In theory, maybe. The idea is to contract space in front of a spacecraft and expand it behind, allowing the ship to ride a wave of warped spacetime. It's a clever workaround, but it would require a substance with negative energy density, a kind of exotic matter we have no evidence for. The energy requirements would also be planet-sized. So, where does that leave us? Despite clever ideas and curious exceptions, nothing with mass or information has ever been observed traveling faster than the speed of light. Every time we think we've found a loophole, the universe calmly closes it. And maybe that's not such a bad thing. The speed of light is like a safety rail, keeping the universe from falling into paradox and chaos. It gives us structure, order, and a kind of cosmic serenity. What if the speed of light isn't just a limit, but a key to understanding space, time, and reality itself? One of the most intriguing ideas in modern physics is that the speed of light is a kind of conversion factor, a bridge between space and time. That number, which we call c, is what lets us translate distance into time and back again. You've probably seen this in Einstein's famous equation, E equals mc squared. Here, c appears as a bridge between mass and energy, but it shows up all over relativity, hinting that it's more than just a speed. It's a kind of universal glue. In Einstein's theory, space and time aren't separate. They're interwoven into a single material, space-time. The speed of light is the conversion rate between the two. This is why you can measure distances in light years. It's a measure of distance, how far light travels in 1 year, but we use a time-based unit to describe it. When we say nothing can go faster than light, we're also saying nothing can mess with the relationship between space and time. The speed of light defines that relationship, holding the whole quilt of reality together. This leads to an even more curious idea. When light travels, it doesn't experience time. From a photon's perspective, the moment it's emitted and the moment it's absorbed happen at the same instant. For something moving at the speed of light, the clock stops altogether. So, light is not just traveling through the universe. It is defining the structure of the universe as it goes. We have even made the speed of light the ruler against which all other rulers are measured. In a universe that can seem vast and strange, there is something beautifully fixed. The speed of light is a constant you can build your world around, because we quite literally do. The speed of light is woven into your everyday life too. Let's start with your phone. Every time you tap the screen or stream a video, you're harnessing light traveling through fiber optic cables. These slender strands of glass form the backbone of the internet, carrying information as tiny pulses of light at nearly light speed. Another technology reliant on light speed is the Global Positioning System, or GPS. Your device connects to satellites, each sending a signal with a precise timestamp. Your GPS receiver compares the arrival times of these signals to figure out your location. But for this to work, we have to account for both special and general relativity. The satellites are moving quickly, so their clocks tick a little slower. At the same time, they are higher up in Earth's gravitational field, which makes their clocks tick a little faster. Without correcting for both of these effects, your GPS would be wrong by several kilometers every single day. Let's zoom in even closer to your eyes. Vision itself is built on light's behavior. You see the world because photons bounce off objects and enter your eye, where they are focused onto your retina. Your brain then reconstructs these signals into a vivid, colorful image. Even the humble microwave oven owes its existence to electromagnetic waves. Microwaves are just a lower frequency form of light. They bounce around inside the oven, causing water molecules in your food to jiggle and heat up. Your favorite radio station, Wi-Fi signals, and Bluetooth connections are all forms of electromagnetic radiation, zipping through space, guided by the same rules that govern starlight. And remember, everything we know about the universe beyond our solar system has been delivered to us by light. Telescopes capture faint photons that have traveled for billions of years, carrying stories about galaxies, nebulas, and the early days of the cosmos. Light isn't just a cosmic phenomenon. It's in your pocket, in your home, and in your eyes. It's the quiet engine of the everyday. Imagine a single beam of light drifting through the vast emptiness of space. That simple, serene image is a glimpse into the very fabric of the universe. Let's begin with one of the most awe-inspiring pieces of light's legacy, the cosmic microwave background, or CMB. This is the oldest light in the universe, traveling for nearly 14 billion years. It's the cooled-down remnant of the moment the universe became transparent, about 380,000 years after the Big Bang. When scientists measure the CMB, they're literally catching photons that have been traveling since the dawn of time. Light doesn't only tell us where we've been, it also binds everything we're experiencing right now. Take photosynthesis. It's the engine behind almost all life on Earth, and it starts when sunlight hits a leaf. Photons strike chlorophyll molecules, triggering a cascade of reactions that store energy. In a very real sense, every meal you've ever eaten started with a photon from the sun. Our very bodies are also built to respond to light. The human circadian rhythm, our internal clock, is deeply influenced by it. A burst of morning light tells your brain to stop producing melatonin, the hormone that makes you sleepy. Fading light in the evening lets that melatonin rise again, nudging you toward rest. But perhaps the most profound thing light does is connect. It's how information travels. Every time we see something, we are receiving messages encoded in waves, shaped by space, and translated by our minds. Light is the language of the universe. This reminds us that we're not separate from the cosmos. The atoms in your body were forged in stars that lit up billions of years ago. You are, quite literally, made of stardust, carried to you by light. And so, this restless traveler, this photon with no mass, no clock, and no home, does more than just move. It connects the ancient past to the present moment. It ties atoms to galaxies. It lets eyes see and minds understand. And so, here we are, gently floating back to where we began. We set out to answer a simple question: why does light have a speed limit? The answer in the end is as elegant as it is profound. Light travels the way it does because the universe is built to let it and to be shaped by it. Its speed is not just fast, it's fundamental. A cosmic rule that holds everything together. It isn't something that can be broken or outpaced, and perhaps that's a good thing. The speed of light gives us order, time, and a way to understand. It gives us stories and sunsets and the warmth of starlight on a cold night. Maybe it's already perfect, just the way it is. And now, as we bring this quiet journey to a close, Let me ask you again, where in the world are you listening from tonight? Wherever you are, and whenever it is, thank you for spending this time with me. If this sleepy exploration with Stellify Science helped you unwind or sparked a quiet sense of wonder, please show your support by giving this video a like and tapping the subscribe button. Your support is what helps more curious minds find this calm corner of the cosmos, and it allows me to continue creating these journeys for you. And if this video kept you awake, well, at least you might have learned something interesting while waiting for sleep to find you. Until next time, rest well, and may your dreams move at just the right speed.